Now, when you run into the uncertainty principle, you might feel like you've been a little bit cheated. This is totally human. Lots of people want to have it all, and the uncertainty principle seems to say fundamentally that we can't. Maybe I was pulling a fast one there. You might think, well, that double slit experiment, yeah, that obeys an uncertainty principle. I can't simultaneously localize the direction of motion, or the speed of the wave, and also its location. But maybe that was a weird artificial experiment. Maybe, for example, with electrons, that's got some mass there, maybe if an electron is going along, I could be a little more clever and figure out a way to cheat and violate the uncertainty principle. For example, suppose I have all kinds of experimental apparatus available. I've got like, is it just a technical problem? I don't have enough fancy equipment? No, it's not a technical problem. For example, suppose that I wanted to see exactly where an electron is traveling and how fast and what energy and so on. I could, for example, hit it with little photons and bounce them off and see where the electron is located and how much energy it has. Here's the problem with that. If I want to get a more accurate reading on the electron's momentum and its position, I'm going to need to hit it with higher energy photons. Uh-oh, what happens then? The act of observing where the electron is, observing it with a photon, that would be one way to see where it is, alters the motion of the electron. It alters the momentum, it alters the speed and direction that the electron was going in, adding uncertainty. So in trying to narrow down the uncertainty in one way, with like my X-ray microscope or whatever, I'm actually increasing the uncertainty another way. You just can't keep it down. It's not anything about the experiment that was set up. It's fundamental to nature. All right, and of course this is very well known that this really bothered Einstein, that there's just a random, unpredictable element. You basically, at a quantum mechanical level, you can only talk about the probabilities of finding a particle there. It doesn't have a precise location, but you can have very well defined mathematical functions that describe the probabilities, for example, of an electron in an atom. In fact, the first description of quantum mechanics, when it was developed in the 1920s and 30s and so on, was called wave mechanics. Quantum mechanics is really wave mechanics applied to particles such as electrons. So, as you know, when you try to confine a wave to a fixed location, you get some very interesting wave effects. In fact, what actually happens? If you really want to confine a wave, I can give you two examples. How about an air wave or a sound wave, and you want to confine it to a box, such as an organ pipe? Well, you're going to get certain standing waves. Only certain frequencies of waves and certain wavelengths of waves will be supported inside that confined space. And so an organ pipe is a very classic example. You build it to the right length, you know what the speed of sound in air is, and that tells you what the fundamental frequency of vibrations of sound waves is going to be in the organ pipe. Another very similar, mathematically similar analogy is transverse waves on a string under tension. That's what a guitar, or a violin, if you're so inclined, does. Right? It's fixed at two ends, and then it's not free to vibrate at the ends, but the string in between is under tension, and what actually happens is waves bounce back and forth at certain frequencies, certain speeds between the fixed ends, and now I'm telling you exactly that same phenomenon happens to electrons when you confine them into an atom, because they're held by the electric attraction of the positively charged nucleus, and they're negatively charged. It makes the world go round here. Now, just to illustrate this with a guitar string, I've got a nice little video here that it's so interesting, I think I'll show it to you. What have we got here? This is basically a big old guitar string in a lab here, and we're going to look at it a little more carefully. So it's just tied down at one end here. I'll show the video in a second. And at this end here, we have a little piston that's just going up and down, trying to vibrate this end of this rope or string or whatever it is here. It's an elastic, stretchy rope that's under tension. And the only thing that's going to happen in this entire demo, aside from some sort of weird music that they decided to play, maybe that's appropriate because we're looking at standing waves and we're listening to music at the same time. I don't know who the artist is in this music, some weird group. So you don't have to pay attention to music. But what you'll notice is the only thing I'm going to change is what the frequency is at which the piston goes up and down. And then you're going to notice an effect that you probably, hopefully, you're familiar with on piano strings and guitar strings and even on organ pipes, which is there is, of course, a fundamental frequency that you're going to see. Here are the two ends of the rope or this guitar string. And so, of course, if you pull the guitar string up like this, the tension will pull it back down. It'll shoot through the equilibrium, go like this. That, of course, is the simplest oscillation. There are no nodes in it except the two ends that are fixed and not moving. And so this oscillation is the fundamental sound or the fundamental frequency of the guitar string. And you can see 1/2 of a wavelength stretches between the two fixed points. But as you probably realize, if you pluck a guitar string properly, you can get an overtone. For example, if you put your finger right in the middle of a guitar string, so you prevent it from vibrating in the middle, you'll get two oscillations that are 180 degrees out of phase happening on either side. On the left side, when the string is oscillating up, the right side will be oscillating down, like this. I better not show it with my hands. Let's look at the video instead. That is the first overtone. It's at exactly twice the frequency. It has exactly half the wavelength. One wavelength then, you may recall this from earlier in Physics 6, one wavelength will be stretched between the 2 points. And if you're really a fancy guitarist, and we're gonna do that on this string here, you can have even higher harmonics, a whole harmonic series. The first harmonic is twice the frequency of the fundamental. That's 1 octave above to musicians. Hope there's some musicians here, or people who like music, even if you don't like this video. But you can have 3 nodes here, or we can have 2 nodes here, not just 1 here, but we can put a node 1/3 of the way in and 1/3 of the way in which case we're going to have 3 times the frequency of the fundamental. That corresponds to 1/5 above. So if you're a musician, middle C might be, depending on the tension of the string, might be the fundamental. High C is the first overtone, the first harmonic. The second one is high G. And then if you have a higher frequency, you go to 3 nodes. You're at 4 times the original frequency. That's double high C. And then the next one is double high F. In fact, the entire musical sequence of notes is just a series of overtones starting with C. Let's look at it. Now, what they do is they increase the frequency that they're driving these motions from a fundamental frequency to higher and higher frequencies. So you'll see higher and higher frequency modes or overtones excited on the string. And then to see it better, because it's hard to see with the lights on, they run a strobe light that flashes at almost the same, but not exactly the same frequency as the oscillations are happening. So you can freeze the oscillations and see how this string is really bent and twisted for these different, for the fundamental and the different overtones. All right, now we're driving it. That's the fundamental. Whoops, higher frequency. You see there's 1 node. That's twice the frequency. That's the first overtone. Let's go faster. Second overtone, triple the frequency. 4 times the frequency there. But you can't see it very well, can you? 5 times. That's the 4th harmonic. And now, whoa, it looks like there's 6 there. I don't know what this guy's singing about. All right. Now we've got a strobe on so that we can... Well, I'm sorry, that was not a strobe. That's a slow motion. See, that's the first overtone. All right, slow motion is useful, but it's still not that easy to see. What we're going to do is we're going to get the strobe light going on. All right. Yeah, make sure this is stable. It's an elastic string. That guy is bugging me. I'm sorry. He's not even singing about physics. All right, so the strobe can go at different frequencies to try to match the overtone frequencies of this string. I don't want to advertise with Google. All right. See what I said? The bottom is, that side is going down while this side's going up. There's one point in the middle that's not moving at all. Right about there is not really moving at all. It's not moving that slowly, obviously. The stroboscope is almost synced to the motion. So that is your first harmonic right there. Now here, this looks like the second harmonic, or third harmonic. Whoa, it's the second harmonic. See? So the middle goes up and the ends go down. Pretty cool, huh? Now we've got it exactly the right frequency. So you can see the actual shape of the string, which is fairly difficult for your eye just isn't fast enough to see these things usually. How cool is that? I kind of like that. Let's see if we're going to tune to any other frequencies besides that one. So you can see that there are two nodes in between where the string doesn't really go up and down. One there, a third of the way down, another one, 2/3 of the way down. All right? Pretty cool. Well, I guess that's all you're going to get to see here, but I do kind of like that. Now, that was just a very simple one-dimensional case. All right, stop. Thank you. All right, you can watch that anytime with the volume cranked up really high or turned off, depending on your preference. But that was just one dimension. What about waves in 2 or 3 dimensions? They also make standing wave patterns. In other words, whenever you confine a wave in a 2-dimensional or even a 3-dimensional volume, you're still going to get the same interference, the same standing wave effects, and here's the important point. Only a limited range of frequencies will be possible. Other frequencies, the wave won't close back on itself and constructively interfere. So I'm not going to show this one, but I absolutely, it takes a little bit of time, but I absolutely require that you look at essentially the same experiment on this video. This video will take your breath away. These are amazing 2-dimensional oscillations. They just take a square metal sheet and vibrate it at like a few thousand times per second, and you get unbelievable 2-dimensional constructive and destructive interference patterns. What they do on this plate, as you'll see, is they put little salt grains. This video uses an awful lot of salt. They pile up the salt over the plate, and what happens is the salt almost immediately moves and piles up at the locations of the plate that aren't moving, at the nodes. And so you can see these beautiful, gorgeous patterns, artistic patterns, are patterns that you can't believe are simply described by mathematical functions. They're somewhat complicated mathematical functions, hypergeometric functions and so on, that we're not going to work on in this class, but they are just math functions, that what happens when you solve the wave equation in 2 or 3 dimensions. Now, what was the point of telling you all this? The same thing that happens on the guitar strings, the same thing that happens on this metal plate that's vibrating, also happens to electrons in an atom. And that's very crucial. So electrons cannot orbit around the nucleus any old way that they want because they're a wave. Here's how electrons actually orbit around. These electron orbits, aside from the first one, that's the lowest or fundamental orbit of the electron, the ground state. That one looks pretty simple, but as soon as you get to slightly higher energies, the orbits start looking pretty weird and pretty complicated. But if you've just watched the video that I urge you to absolutely watch that first, then these weird electron orbital clouds are actually going to look rather familiar. Some of them look not that different from these, except these are in 3 dimensions now. So here's where the analogy that some people might have, oh, the nucleus, it's positively charged and attracts the electron and orbit around. Isn't that just like how planets orbit around the sun? You know, it's an inverse square law force. Gravity's inverse square law force. The Coulomb force is inverse square law force. The force falls off as 1 over the separation squared of the charges or the masses. No, that's where things end. It's totally different on a quantum mechanical scale because, in principle, an asteroid or a spacecraft or anything could have any size orbit, any kind of circle or ellipse that it wants to around the sun. But that is absolutely not possible for an electron, in this case, orbiting around a proton. Oh, what atom is this? I'm showing one electron orbiting in a hydrogen atom. It's the simplest atom. And of course, if I had 2 electrons going around a +2 charge, that would be helium, the orbits get more complicated than this. You think this is complicated. This is nothing. This is very simple. The orbits will get more and more complicated, although they have a lot of patterns and similarities in them. There's always a ground state, which is when the electron is closest to the proton and has the lowest amount of energy. If you add more energy, just like, you know, in going around the solar system, you can go in a bigger orbit. Those are high energy orbits. But nothing in between is allowed. This is kind of the energy of these orbits is like a staircase. You can be on the lowest step, the ground floor. You can step up to one higher excited energy level. You can step up to 2 energy level. So that's even a higher excited state. And what actually happens? As you add more energy to this electron, it can only jump. It can't be in between. You can't be in between a stair. You can be either up one stair, that's an excited state where the electrons are high energy. You can be up a higher stair, that's a higher excited state, but nowhere in between is allowed. The electron can't stay there. In other words, just like you found with guitar strings, the energy orbitals of electrons are quantized. They have to be because they're waves. That is why wave mechanics is quantum mechanics. And I'm showing you, these are actual pictures. This is not just some artist's conception. These are actual computer-generated pictures using the formulas. And you'll notice some weird stuff about these electrons. The more energy there is in the electron orbit, the more chance there is of finding the electron further away from the center, as you'd kind of expect qualitatively. That's kind of what you'd expect classically if this were a planet going around the sun. But here's weird things. There's interference patterns of destructive interference where, look at that black band there. There is no probability that the electron will ever be found right there in that ring. That is 0 probability. It's like a dark interference node. It is a dark interference node. You've seen these in optics too, where the light interferes. There's a dark node here. There's no probability of finding the electron here, but there is a probability of finding it further out at a larger radius. And there's a probability of finding it at a smaller radius. This is talking about the same electrons in the same orbit. And there's another probability of finding it close to the center here. What the heck is going on? Now you see that our ideas about planets orbiting the sun totally break down because the electrons simultaneously could be found in different locations that aren't even connected. How the heck did it get across from here to here? Or from here to here? It can never be found in between. This is for one actual state or one actual orbit and energy of the electron. It's because, sorry, you're thinking about a particle that moves around. That is so not quantum mechanical. It just is. It's a cloud of probabilities. To say that with my hands there. It's a cloud of probability, and these are the probabilities of where you will find that one electron. The electron is simultaneously at all of those places. If you want to really be zen about it, it is all of those places and not there. It is, some of it is there, some of it's there. It's like a cloud of probability, which isn't even continuous. It's just continuous. What about these other beautiful little rosette patterns and so on? That is when the electron has, when its orbit has a certain angular momentum or spin going around the nucleus in the center. And that also changes its orbit, just the same way that changing the angular momentum of an orbit of a planet is going to change it. But again, it does it in these discrete, quantized ways, depending on what the direction of the spin is. So you don't need to calculate any of this stuff. You just have to understand that even a very simple system, single electron orbiting a proton in a hydrogen atom, has a whole series of possible different energy levels, which I could draw like on a ladder. from the lowest ground state energy to some quite high energy levels, because these correspond to different three-dimensional standing waves of the electron. And here's the fun part. The electron can jump up from a low energy to a high energy, up to a high energy, if it could acquire exactly the precise energy difference to go from here to here or here to here. If it got just the right energy to climb that next stair, it could jump up to higher road. Or if it had more energy, it might jump all the way from the first level to the third level. If you had enough energy, if you had exactly the right amount of energy, it could do that too. How could it get exactly the right amount of energy provided to it? If it had a photon of exactly the right amount of energy, a little bundle of photon energy equaling h times f, if you got exactly the right frequency of the photon, that might correspond to exactly this energy difference here. I can tell you exactly what that energy difference is. It is about 10 electron volts to go from here to here. And then going up to here is another 3 electron volts. Anyway, that each of these energy transitions corresponds to a particular photon, a quantized packet of energy. And understanding what you observe when the electrons change these levels is the heart of spectroscopy. It's really the key to a quantum mechanical understanding of atoms. All right, I just put this diagram in here to show that even a simple electron, this is kind of weird. Actually, the angular momentum of an electron can only come in certain quantized amounts. Not just the energy of the orbit, but also the angular momentum of an electron. Basically, I think the proper interpretation of that is that space is quantized on small scales. And so an electron can't just have random amounts of angular momentum. It has to have angular momentum vectors of certain quantized amounts. They're quantized in units of h over 2 pi, in case you're curious. Anyway, I'm not expecting you to know that, but this is the reason why even a simple electron and a simple atom has many different energy levels, many different orbits that it could find itself in, and it could be transiting from one to another with either the absorption, the taking in energy, or giving off energy if it wants to drop to a lower energy level. Let's see. This is really just the same as my earlier graph here. It's just showing it in blue, these probability clouds. So I think I sort of already told you this. We're really getting into chemistry now. There's your ground state level. 1s is what it's called. Here's the first excited state, but no angular momentum in this case. If you add a little bit of angular momentum, the electron wants to be like this because the angular momentum is going this way. If the angular momentum is going this way in the opposite direction, then here are the two probable locations that you might find the electron. So that has, let's see, there's more energy and you get more complicated things here. So as we go like from ground state, we're going up to higher energies like this, and then we're changing the amount of angular momentum here. I don't need to know that. All right, so I think I've really beaten this one pretty well. This is a profound fundamental difference between a solar system where any particle or object can orbit anywhere it wants to. Electrons orbiting in atoms are in these fixed quantized orbits. And they're either in the ground state or they're in an excited state, and it's very analogous mathematically to the overtones that you can pluck a string with. You can pluck this atom with various overtones. If you give it more energy, you can get to high overtones, but nothing in between. You know, on that guitar string, if it's tuned to middle C, you can get a middle C out of it if you pluck it the right way. If you pluck it the right way, you can get a high C, you can get a high G, you can get a high F, but not things in between middle C and high C. It won't vibrate that way. That is not a standing wave, which is allowed because on the guitar string, same as with an electron and an atom. All right, let's do a simple calculation here, and then we're going to be done. The energy of an electron, of course, classically, according to like Newton's laws and Coulomb's laws here, is the product of the two electric charges, the proton times the electron. They both have an electric charge E. It's the same as the charge, the proton is the same as the electron. E squared over r is the electric potential energy of having those two charges close together. Now, I just spent quite a bit of time saying, yeah, actually there's not one fixed r that the electron's at. Yeah, that's true. But there's an average r. The average probability says that the electron's going to be, and it's pretty small. R is very small. So even though E is pretty small and E squared is pretty small, R is really small. It's basically dictated by the uncertainty principle. The uncertainty principle prevents the electron from getting closer to the nucleus than it does, because that would violate the uncertainty principle for waves. So as a result, R is very small. Now, I already told you earlier that a good way to measure this E squared over R, I don't want to do this in joules. That would be ridiculous. That's a teensy tiny number, like 30 zeros there. That's stupid. Let's use electron volts, which I defined earlier. There it is, 1.6 times 10 to the minus 19 joules. That you might think is small. That'd be very small compared to any kind of macroscopic measurement that we'd want to make, where usually it takes like a joule to get our attention. As humans or whatever, some fraction of that. But if you're talking about an individual atom, 1 electron volt does get its attention. A few electron volts would be enough to actually move those electrons from one energy orbit to another. They could go from the ground state, or the fundamental, up to an excited overtone. Or they could go from the first excited overtone to the second overtone. Or, if there's enough energy, quite a few electron volts, actually turns out like maybe more than 10 electron volts, 5 or 10 electron volts, the electron could escape altogether and be kicked out of the atom. So if you're an electron and you're looking at photons of a few electron volts in energy coming by, that can really make a big difference. That can change your whole day. So not a lot of energy for a human, but a huge amount of energy when seen by one atom. All right, so let's just do a simple calculation first. To get, just say, 1 electron volt, which is a kind of a minimal amount of energy that will start really having major effects on electrons, what frequency would that correspond to? What photon, according to Planck's formula, we just have to do a little bit of bookkeeping to convert, between frequency measured in cycles per second and joules, use this formula and convert to electron volts so we can answer number 1. Now, let's look at another question. Suppose that an electron were just freely traveling around in space. It's escaped from its individual atom, which we call ionization. So you have an ion, and 1 electron is floating around freely. Give it this energy. Give it 1 electron volt. Give it 1.6 times 10 to the minus 19 joules. What kinetic energy does that correspond to? How fast would it be going? That's another simple calculation. And finally, let's compare that answer to the typical kinetic energy that particles now have right now in this room. It's about room temperature in here. And so we know that if there were free electrons, there's a few of them in here, or any kind of particle, equal partition says that they would have approximately a kinetic energy of 3/2 kT. Remember, that was on the second midterm, that problem. And so I want to compare that to the answer to 1 electron volt. All right, so these are simple problems. Now that we know our definitions and our formulas, this is the kind of thing that could pop up on exam. So I'll give you the answers pretty quickly here. Here is your formula. This is h divided by the momentum. So this is the wavelength. By the way, this works for photons and it also works for electrons, right? This is basically the Planck formula. This is a restatement of E equals hf, isn't it? Well, let's do it then, except I decided to solve for the wavelength. So the wavelength of a photon having 1 electron volt, well, there's h, there's the speed of light. I have to divide by how many, this was in joules, so I have to divide by how many joules there are in electron volts. So I'm dividing by a very small number. Anyway, I get a pretty short wavelength here of 1/1,000,000 of a meter is about what that is. And that is 1 micron, 1 micrometer. Aha! That's just at the far red end of the spectrum. So, for example, green light in the visible that we can clearly see consists of photons of a half micron wavelength. And so what is the energy of these little packets or little bundles of energy called photons of green photons? It's about 2 electron volts. It's about twice the energy and half the wavelength of this. So we've already learned something interesting. It's very interesting, very important. What did we learn? The wavelengths of visible photons that you can see, such as green light, yellow light, orange light, correspond to a substantial amount of energy, a few electron volts, several electron volts. If you go up to the blue end of the spectrum, you're dealing with maybe 4 electron volts. And as you go into the ultraviolet, 5, 6, 7, 8, 10 electron volts. So visible light photons are going to be able to have major effects on electrons inside an atom, because I already told you, a few electron volts is a big deal for an atom. All right, how about how fast would an electron be going when it picks up an electron volt? I'm just using energy here. There's the energy right there in joules. Energy is equal to 1/2 mv squared. So all I have to do is take the energy, divide by the mass of an electron, which in kilogram units, I'm doing everything in kilogram joules units, meters, kilograms. There's the mass of an electron. Very small. That's the whole point. So if it has a joule of energy, it's going to be going pretty fast. And then I have to take the square root of this. I think I left a factor of 2. There's a 2 in there. Anyway, I don't even care about square roots of 2 here. I just want to get a rough idea of how fast an electron is going when it has 1 electron volt. Darn, because it's such a small mass in the denominator, that turned out to be really fast. Whoa, it's going 30,000 meters per second. That's like some, significant percentage of the speed of light. Wow. And I'm telling you, that's happening all the time. That's the normal speed at which electrons move around when they're in orbits in atoms. Why? Because they're very small orbits, and so the electric attractive force, at least compared to an electron, is a lot. Now, let's contrast that. So anyway, inside atoms, electrons move around very fast. How about if particles in this room? We're just at room temperature here. How fast are they going? Well, let's figure out, in other words, how much energy is 3/2 kT. You may have already done this calculation. I'm going to do it again. I'm going to do it exactly right. There's 3/2, it's 1.5. There's K, that's our Boltzmann constant. That's going to be an energy per degree Kelvin. So that's very small energy there, 10 to the minus 23 joules. And then how many degrees Kelvin? Well, let's just say roughly it's 300 degrees in here, Kelvin. Actually, it's not that hot. I'd be sweating. It's like 280 or whatever. But they're close enough, all right? So let's see, 300, that's like 2 times, that's a 2 times 300 is 600. 600 times 10 to the minus 23 is the answer. 6 times 10 to the minus 21 joules. So how does that compare to an electron volt? A lot less. So the typical energies of particles that are moving around in this room are like 30 times less than the energy of those particles when they get inside atoms. What is the practical consequence of that? I just told you something that has huge consequences for how everything works in the world. This one fact that I told you. What does that mean? Here's your philosophy slide, then we're done. The energy of an electron orbiting in an atom, E squared over R, is a large amount of energy compared to the energies you find here at room temperature. It's going much faster than the molecules are just bouncing around at room temperature. It's going much faster than I am when I walk around the room. That is why when you change the electron energies, when you rearrange the electron orbitals, you're getting big changes in energy if you do it on a mass scale. If you reorganize the electric bonds, well, actually the chemical bonds for a chemist in molecules, for example, you change the electron orbits, and you do this for a whole lump of material, large amounts of energies are going to be released, because E squared over R is a large amount of energy for electrons. Heck, they're going, like I said, at a few percent the speed of, almost 1% the speed of light there. So if I tap in that chemical energy and then, for example, give it to some object, such as a car, there's a lot of energy available. So the fact that things are moving so fast with such high energy in these chemical and electron orbital bonds means, for example, that is why it only takes the chemical energy in like 1 cup of gasoline to move my car, which is, I don't know, more than a ton. Wow. So it takes like, I don't know, 10 or 15 ounces of gas, release that chemical energy, release a lot of that E squared over R through the right changes and rearrangements of the electron orbits, and I can move something that is, I don't know, thousands and thousands of times more mass. Wow. Isn't that amazing? That's why basically humans really couldn't do hardly anything interesting until we started tapping this chemical energy, largely in fossil fuels. But that raises another interesting question. So there's a tremendous amount of energy locked up in electron orbits in molecules. How about if we went even closer in, much smaller than R? Electrons can't get too close because of the uncertainty principle. They can't get too close to the positively charged nucleus. What about the positive charges inside the nucleus that we're going to talk about extensively in the final week of this course? There, the R is thousands of times smaller than for the size of an atom. The size of an atom, we mean sort of the typical size of those electron orbitals. The size of a nucleus is thousands of times smaller, therefore the electric forces and the electric energies involved in the nucleus of an atom are thousands or millions of times larger than the chemical energies I just told you about. So instead of using a cup of gasoline, for example, to move my car, I could use 1,000th of this, or actually I could use 1,000,000th of this if I could tap the nuclear energy of it. For example, through radioactive decays, or through a fission or a fusion nuclear reaction that reorganizes particles in the nucleus. A tiny amount, the energy locked up in a thimbleful or less of material could drive my car around pretty much for a year. So there are literally enough energy in a cup, in the nuclear energy of a cup of material can literally move around kilotons. In fact, you might measure the energy of nuclear power in kilotons of energy, because that means kilotons of TNT, because that's typically what's in it.